Learning objectives. In this chapter, the user will learn the following in detail. Basic illumination models, diffuse reflection, specular reflection and Phong model, Von model, intensity attenuation, color considerations, transparency, shadows, displaying light intensities, halftone patterns and dithering techniques, polygon rendering methods, go-rod shading, Phong shading, ray tracing methods, problems with interpolated shading, bump mapping. Basic illumination models. Realistic displays of a scene are obtained by generating perspective projections of objects and by applying natural lighting effects to the visible surfaces. An illumination model, also called a lighting model, is sometimes referred to as a shading model, is used to calculate the intensity of light that we should see at a given point on the surface of an object. A surface rendering algorithm uses the intensity calculations from an illumination model to determine the light intensity for all projected pixel positions for the various surfaces in a scene. Surface rendering can be performed by applying the illumination model to every visible surface point, or the rendering can be accomplished by interpolating intensities across the surfaces from a small set of illumination model calculations. Basic illumination models. The empirical models described in this section provide simple and fast methods for calculating surface intensity at a given point, and they produce reasonably good results for most scenes. Lighting calculations are based on the optical properties of surfaces, the background lighting conditions, and the light source specifications. Optical parameters are used to set surface properties such as glossy, matte, opaque, and transparent. This controls the amount of reflection and absorption of incident light. All light sources are considered to be point sources, specified with a coordinate position and an intensity value, color. Ambient light. A surface that is not exposed directly to a light source still will be visible if nearby objects are illuminated. In our basic illumination model, we can set a general level of brightness for a scene. This is a simple way to model the combination of light reflections from various surfaces to produce a uniform illumination called the ambient light or background light. Ambient light has no spatial or directional characteristics. The amount of ambient light incident on each object is a constant for all surfaces and over all directions. We can set the level for the ambient light in a scene with the parameter IA, and each surface is then illuminated with this constant value. The resulting reflected light is a constant for each surface, independent of the viewing direction and the spatial orientation of the surface, but the intensity of the reflected light for each surface depends on the optical properties of the surface, that is, how much of the incident energy is to be reflected and how much to be absorbed. Bump mapping. A better method for creating surface bumpiness is to apply a perturbation function to the surface normal and then use the perturbed normal in the illumination model calculations. This technique is called bump mapping. If P of U and V represents a position on a parametric surface, we can obtain the surface normal at that point with the calculation N equals PU into PV, where Pu and Pv are the partial derivatives of P with respect to parameters U and V. To obtain a perturbed normal, we modify the surface position vector by adding a small perturbation function called the bump function. P dash of U, V equals P of U, V plus B of U, V into N. This adds bumps to the surface in the direction of the unit surface normal. N equals capital N divided by mod of capital N. The perturbed surface normal is then obtained as N dash equals Pu dash into Pv dash. We calculate the partial derivative with respect to U of the perturbed position vector as Pu dash equals dou of P plus Bn over dou U equals Pu plus Bun plus Bnu. Assuming the bump function B to be small, we can neglect the last term and write Pu dash is approximately equal to PU plus BUN. Similarly, PV dash equal to PV plus BVN. And the perturbed surface normal is N dash equals PU into PV plus BV into PU into N plus BU into N into PV plus BU BV into N into N. But N into N is 0, so that N dash equals N plus BV into PU into N plus BU into N into PV. The final step is to normalize N dash for use in the illumination model calculations. There are several ways in which we can specify the bump function B, U, V. We can actually define an analytic expression, but bump values are usually obtained with table lookups. With a bump table, values for B can be obtained quickly with linear interpolation and incremental calculations. Partial derivatives BU and BV are approximated with finite differences. The bump table can be set up with random patterns, regular grid patterns, or character shapes. Random patterns are useful for modeling irregular surfaces, such as raisin, while a repeating pattern could be used to model the surface of an orange, for example. To anti-alias, we subdivide pixel areas and average the computed subpixel intensities. This figure shows examples of surfaces rendered with bump mapping. An example of combined surface rendering methods is given in this figure. Color considerations. Most graphics displays of realistic scenes are in color, but the illumination model we have described so far considers only monochromatic lighting effects. To incorporate color, we need to write the intensity equation as a function of the color properties of the light sources and object surfaces. For an RGB description, each color in a scene is expressed in terms of red, green, and blue components. We then specify the RGB components of light source intensities and surface colors, and the illumination model calculates the RGB components of the reflected light. One way to set surface colors is by specifying the reflectivity coefficients as 3-element vectors. The diffuse reflection coefficient vector, for example, would then have RGB components KDR, KDG, and KDB. If we want an object to have a blue surface, we select a non-zero value in the range from 0 to 1 for the blue reflectivity component, KDB, while the red and green reflectivity components are set to 0. KDR equals KDG equals 0. Any non-zero red or green components in the incident light are absorbed and only the blue component is reflected. The intensity calculation for this example reduces to the single expression as shown on the screen. Surfaces typically are illuminated with white light sources, and in general we can set surface color so that the reflected light has non-zero values for all 3 RGB components. Calculated intensity levels for each color component can be used to adjust the corresponding electron gun in an RGB monitor. In his original specular reflection model, Phong set parameter Ks to a constant value independent of the surface color. This produces specular reflections that are the same color as the incident light, usually white, which gives the surface a plastic appearance. For a non-plastic material, the color of the specular reflection is a function of the surface properties and may be different from both the color of the incident light and the color of the diffuse reflections. We can approximate specular effects on such surfaces by making the specular reflection coefficient color dependent. This figure illustrates color reflections from a matte surface. The following figures show color reflections from metal surfaces. Light reflections from a teapot with reflectance parameters set to simulate brushed aluminum surfaces and rendered using Monte Carlo ray tracing methods. Light reflections from trombones with reflectance parameters set to simulate shiny brass surfaces. Light reflections from object surfaces due to multiple colored light sources is shown in this figure. Another method for setting surface color is to specify the components of diffuse and specular color vectors for each surface while retaining the reflectivity coefficients as single-valued constants. For an RGB color representation, for instance, the components of these two surface color vectors can be denoted as SDR, SDG, SDB, and SSR, SSG, and SSB. The blue component of the reflected light is then calculated as shown on the equation on screen. This approach provides somewhat greater flexibility once surface color parameters can be set independently from the reflectivity values. Other color representations beside RGB can be used to describe colors in a scene. For now, we can simply represent any component of a color specification with its spectral wavelength lambda. Intensity calculations can then be expressed as per equation shown on screen. Diffuse reflection. Ambient light reflection is an approximation of global diffuse lighting effects. Diffuse reflections are constant over each surface in a scene, independent of the viewing direction. The fractional amount of the incident light that is diffusely reflected can be set for each surface with parameter Kd, the diffuse reflection coefficient, or diffuse reflectivity. Parameter Kd is assigned a constant value in the interval 0 to 1, according to the reflecting properties we want the surface to have. If we want a highly reflective surface, we set the value of Kd near 1. This produces a bright surface with the intensity of the reflected light near that of the incident light. To simulate a surface that absorbs most of the incident light, we set the reflectivity to a value near 0. Actually, parameter Kd is a function of surface color, but for the time being we will assume Kd is a constant. If a surface is exposed only to ambient light, we can express the intensity of the diffuse reflection at any point of the surface as I amdiff equals Kd into Ia. Since ambient light produces a flat, uninteresting shading for each surface, scenes are rarely rendered with ambient light alone. At least one light source is included in a scene, often as a point source at the viewing position. We can model the diffuse reflections of illumination from a point source in a similar way. That is, we assume that the diffuse reflections from the surface are scattered with equal intensity in all directions, independent of the viewing direction. Such surfaces are sometimes referred to as ideal diffuse reflectors. They are also called Lambertian reflectors, since radiated light energy from any point on the surface is governed by Lambert's cosine law. This law states that the radiant energy from any small surface area dA in any direction phi n relative to the surface normal is proportional to cos phi n. The light intensity, though, depends on the radiant energy per projected area perpendicular to direction phi n, which is dA cos phi n. Thus, for Lambertian reflection, the intensity of light is the same over all viewing conditions. Even though there is equal light scattering in all directions from a perfect diffuse reflector, the brightness of the surface does depend on the orientation of the surface relative to the light source. A surface that is oriented perpendicular to the direction of the incident light appears brighter than if the surface were tilted at an oblique angle to the direction of the incoming light. This is easily seen by holding a white sheet of paper or smooth cardboard parallel to a nearby window and slowly rotating the sheet away from the window direction. As the angle between the surface normal and the incoming light direction increases, less of the incident light falls on the surface, as shown in the figure. The above figure shows a beam of light rays incident on two equal area plane surface patches with different spatial orientations relative to the incident light direction from a distant source, parallel incoming rays. If we denote the angle of incidence between the incoming light direction and the surface normal as theta, then the projected area of a surface patch perpendicular to the light direction is proportional to cos theta. Thus, the amount of illumination, or the number of incident light rays cutting across a projected surface patch, depends on cos theta. If the incoming light from the source is perpendicular to the surface at a particular point, that point is fully illuminated. As the angle of illumination moves away from the surface normal, the brightness of the point drops off. If IL is the intensity of the point light source, then the diffuse reflection equation for a point on the surface can be written as IL diff equals to KD IL cos theta. A surface is illuminated by a point source only if the angle of incidence is in the range of 0 to 90 degrees. Cos theta is in the interval from 0 to 1. When cos theta is negative, the light source is behind the surface. If n is the unit normal vector to a surface and L is the unit direction vector to the point light source from a position on the surface, then cos theta equals n into L, and the diffuse reflection equation IL diff equals KD IL into NL. Reflections for point source illumination are calculated in a world coordinates or viewing coordinates before shearing and perspective transformations are applied. These transformations may transform the orientation of normal vectors so that they are no longer perpendicular to the surfaces they represent. This figure illustrates the application to positions over the surface of a sphere using various values of parameter KD between 0 and 1. Each projected pixel position for the surface was assigned an intensity as calculated by the diffuse reflection equation for a point light source. The renderings in the figure illustrate single point source lighting with no other lighting effects. This is what we might expect to see if we shined a small light on the object in a completely darkened room. For general scenes, however, we expect some background lighting effects in addition to the illumination effects produced by a direct light source. We can combine the ambient and point source intensity calculations to obtain an expression for the total diffuse reflection. In addition, many graphics packages introduce an ambient reflection coefficient Ka to modify the ambient light intensity Ia for each surface. This simply provides us with an additional parameter to adjust the light conditions in a scene. Using parameter Ka, we can write the total diffuse reflection equation as I diff equals Ka Ia plus Kd Il into Nl, where both Ka and Kd depend on surface material properties and are assigned values in the range from 0 to 1. This figure shows a sphere displayed with surface intensities for values of parameters Ka and Kd between 0 and 1. Displaying light intensities. Values of intensity calculated by an illumination model must be converted to one of the allowable intensity levels for the particular graphic system in use. Some systems are capable of displaying several intensity levels, while others are capable of only 2 levels for each pixel, on or off. In the first case, we convert intensities from the lighting model into one of the available levels for storage in the frame buffer. Assigning intensity levels. We first consider how grayscale values on a video monitor can be distributed over the range between 0 and 1 so that the distribution corresponds to our perception of equal intensity intervals. We perceive relative light intensities the same way that we perceive relative sound intensities on a logarithmic scale. This means that if the ratio of the two intensities is the same as the ratio of two other intensities, we perceive the difference between each pair of intensities to be the same. As an example, we perceive the difference between intensities of 0.2 and 0.22 to be the same as the difference between 0.8 and 0.88. Therefore, to display n plus 1 successive intensity levels with equal perceived brightness, the intensity levels on the monitor should be spaced so that the ratio of successive intensities is constant. That is, I1 over I0 equals I2 over I1 and so on, up to In over In minus 1 equals R. Here we denote the lowest level that can be displayed on the monitor as I0 and the highest as In. Any intermediate intensity can then be expressed in terms of I0 as Ik equals R to the power of k into I0. We can calculate the value of R given the values of I0 and n for a particular system by substituting k equals n in the preceding expression. Since In equals 1, we have R equals 1 over I naught raised to the power of 1 by n. Thus, the calculation for ik can be rewritten as ik equals I naught raised to the power of n minus k into n. As an example, if I naught is equal to 1 by 8 for a system with n equal 3, we have r equals 2 and the four intensity values are 1 by 8, 1 by 4, 1 by 2 and 1. The lowest intensity value I naught depends on the characteristics of the monitor and is typically in the range from 0.005 to around 0.025. A black region displayed on a monitor will always have some intensity value above 0 due to reflected light from the screen phosphors. For a black and white monitor, the 8 bits per pixel, n equals 255 and I naught equals 0.01, the ratio of successive intensities is approximately r equals 1.0182. The approximate values for the 256 intensities on the system are 0.0100, 0.0102, 0.0104, 0.0106, 0.0107, 0.0109 and so on, up to 0.9821 and 1.00. With the color system, we set up intensity levels for each component of the color model. Using the RGB model, for example, we can relate the blue component of intensity at level K to the lowest attainable blue value, and N is the number of intensity levels. Similar expressions hold for other color components. Gamma correction and video lookup tables. Another problem associated with the display of calculated intensities is the non-linearity of display devices. Illumination models produce a linear range of intensities. The RGB color 0.25, 0.25, 0.25 obtained from a lighting model represents one half the intensity of the color 0.5, 0.5, 0.5. Usually these calculated intensities are then stored in an image file as integer values with 1 byte for each of the three RGB components. This intensity file is also linear, so that a pixel with the value 64, 64, 64 has one half the intensity of a pixel with the value 128, 128, 128. A video monitor is a non-linear device. If you set the voltages for the electron gun proportional to the linear pixel values, the displayed intensities will be shifted according to the monitor response curve shown in this figure. To correct for monitor non-linearities, graphics systems use a video lookup table that adjusts the linear pixel values. The monitor response curve is described by the exponential function I equals A into V raised to the power gamma. Parameter I is the displayed intensity and parameter V is the input voltage. Values for parameters A and gamma depend on the characteristics of the monitor used in the graphics system. Thus, if you want to display a particular intensity value I, the correct voltage value to produce this intensity is V equals I by A raised to the power of 1 by gamma. This equation is used to set up the video lookup table that converts integer pixel values in the image file to values that control the electron gun voltages. This calculation is referred to as gamma correction of intensity. Monitor gamma values are typically between 2 and 3. The National Television System Committee NTSC signal standard is gamma equals 2.2. This figure shows a gamma correction curve using the NTSC gamma value. We can combine gamma correction with logarithmic intensity mapping to produce a lookup table that contains both conversions. If I is an input intensity value from an illumination model, we first locate the nearest intensity Ik. Alternatively, we could determine the level number for this intensity value with the calculation K equals round log R I over I naught. Then we compute the intensity value at this level. Once we have the intensity value Ik, we can calculate the electron gun voltage Vk equals Ik over A raised to the power of 1 over gamma. Values Vk can then be placed in the lookup tables and values for k would be stored in the frame buffer pixel positions. If a particular system has no lookup table, computed values for Vk can be stored directly in the frame buffer. The combined conversion to a logarithmic intensity scale followed by calculation of the Vk is also sometimes referred to as gamma correction. If the video amplifiers of a monitor are designed to convert the linear input pixel values to electron gun voltages, we cannot combine the two intensity conversion processes. In this case, gamma correction is built into the hardware, and the logarithmic values Ik must be pre-computed and stored in the frame buffer or the color table. Displaying continuous tone images. High-quality computer graphics systems generally provide 256 intensity levels for each color component, but acceptable displays can be obtained for many applications with fewer levels. A 4-level system provides minimum shading capability for continuous tone images, while photorealistic images can be generated on systems that are capable of from 32 to 256 intensity levels per pixel. This figure shows a continuous tone photograph displayed with various intensity levels. When a small number of intensity levels are used to reproduce a continuous tone image, the borders between the different intensity regions, called contours, are clearly visible. In the 2-level reproduction, the features of the photograph are just barely identifiable. Using 4 intensity levels, we begin to identify the original shading patterns, but the contouring effects are glaring. With 8 intensity levels, contouring effects are still obvious, but we begin to have a better indication of the original shading. At 16 or more intensity levels, contouring effects diminish and the reproductions are very close to the original. Reproductions of continuous tone images using more than 32 intensity levels show only very subtle differences from the original. Halftone patterns and dithering techniques. When an output device has a limited intensity range, we can create an apparent increase in the number of available intensities by incorporating multiple pixel positions into the display of each intensity value. When we view a small region consisting of several pixel positions, our eyes tend to integrate or average the fine detail into an overall intensity. Bi-level monitors and printers in particular can take advantage of this visual effect to produce pictures that appear to be displayed with multiple intensity values. Continuous tone photographs are reproduced for publication in newspapers, magazines, and books with a printing process called halftoning, and the reproduced pictures are called halftones. For a black and white photograph, each intensity area is reproduced as a series of black circles on a white background. The diameter of each circle is proportional to the darkness required for that intensity region. Darker regions are printed with larger circles and lighter regions are printed with smaller circles, more white area. This figure shows an enlarged section of a grayscale halftone reproduction. Color halftones are printed using dots of various sizes and colors as shown in this figure. Book and magazine halftones are printed on high-quality paper using approximately 60 to 80 circles of varying diameter per centimeter. Newspapers use lower quality paper and lower resolution, about 25 to 30 dots per centimeter. Halftone approximations. In computer graphics, halftone reproductions are approximated using rectangular pixel regions called halftone patterns or pixel patterns. The number of intensity levels that we can display with this method depends on how many pixels we include in the rectangular grids and how many levels a system can display. With n by n pixels for each grid on a bi-level system, we can represent n squared plus 1 intensity levels. This figure shows one way to set up a pixel to represent 5 intensity levels that could be used with a bi-level system. In pattern 0, all pixels are turned off. In pattern 1, 1 pixel is turned on, and in pattern 4, all 4 pixels are turned on. An intensity value I in a scene is mapped to a particular pattern according to the range listed below each grid shown in the figure. Pattern 0 is used for 0 less than or equal to I less than 0.2, pattern 1 for point 2 less than or equal to I less than 0.4, and pattern 4 is used for 0.8 less than or equal to I less than or equal to 1.0. With 3 by 3 pixel grids on a bi-level system, we can display 10 intensity levels. One way to set up the 10 pixel patterns for these levels is shown in this figure. Pixel positions are chosen at each level so that the patterns approximate the increasing circle sizes used in halftone reproductions. That is, the on pixel positions are near the center of the grid for lower intensity levels and expand outward as the intensity level increases. For any pixel grid size, we can represent the pixel patterns for the various possible intensities with a mask of pixel position numbers. As an example, the following mask can be used to generate the 9 3 by 3 grid patterns for intensity levels above 0. To display a particular intensity with level number k, we turn on each pixel whose position number is less than or equal to k. Although the use of n by n pixel patterns increases the number of intensities that can be displayed, they reduce the resolution of the displayed picture by a factor of 1 by n along each of the x and y axes. A 512 by 512 screen area, for instance, is reduced to an area containing 256 by 256 intensity points with 2 by 2 grid patterns. And with 3 by 3 patterns, we would reduce the 512 by 512 area to 128 intensity positions along each side. Another problem with pixel grids is that subgrid patterns become apparent as the grid size increases. The grid size that can be used without distorting the intensity variations depends on the size of a displayed pixel. Therefore, for systems with lower resolution, fewer pixels per centimeter, we must be satisfied with fewer intensity levels. On the other hand, high-quality displays require at least 64 intensity levels. This means that we need 8 by 8 pixel grids, and to achieve a resolution equivalent to that of halftones in books and magazines, we must display 60 dots per centimeter. Thus, we need to be able to display 60 by 8 equals 480 dots per centimeter. Some devices, for example high-quality film recorders, are able to display this resolution. Pixel grid patterns for halftone approximations must also be constructed to minimize contouring and other visual effects not present in the original scene. Contouring can be minimized by evolving each successive grid pattern from the previous pattern. That is, we form the pattern at level k by adding an on position to the grid pattern at level k-1. Thus, if a pixel position is on for one grid level, it is on for all higher levels. We can minimize the introduction of other visual effects by avoiding symmetrical patterns. With a 3 by 3 pixel grid, for instance, the third intensity level of above 0 would be better represented by the pattern in this figure A than by any of the symmetrical arrangements in figure B. The symmetrical patterns in this figure would produce vertical, horizontal, or diagonal streaks in any large area shaded with intensity level 3. For hard copy output on devices such as film recorders and some printers, isolated pixels are not effectively reproduced. Therefore, a grid pattern with a single on pixel or one with isolated on pixels, as in this figure, should be avoided. Halftone approximations also can be used to increase the number of intensity options on systems that are capable of displaying more than 2 intensities per pixel. For example, on a system that can display 4 intensity levels per pixel, we can use 2 by 2 pixel grids to extend the available intensity levels from 4 to 13. This figure shows one way to assign the pixel intensities to obtain the 13 distinct levels. Intensity levels for individual pixels are labeled 0 through 3, and the overall levels for the system are labeled 0 through 12. Similarly, we can use pixel grid patterns to increase the number of intensities that can be displayed on a color system. As an example, suppose we have a 3-bit per pixel RGB system. This gives 1 bit per color gun in the monitor, providing 8 colors, including black and white. Using 2 by 2 pixel grid patterns, we now have 12 phosphor dots that can be used to represent a particular color value as shown in this figure. Each of the 3 RGB colors has 4 phosphor dots in the pattern which allows 5 possible settings per color. This gives us a total of 125 different color combinations. Dithering techniques. The term dithering is used in various contexts. Primarily, it refers to techniques for approximating halftones without reducing resolution, as pixel grid patterns do. But the term is also applied to halftone approximation methods using pixel grids, and sometimes it is used to refer to color halftone approximations only. Random values added to pixel intensities to break up contours are often referred to as dither noise. Various algorithms have been used to generate the random distributions. The effect is to add noise over an entire picture, which tends to soften intensity boundaries. Ordered dither methods generate intensity variations with a one-to-one mapping of points in a scene to the display pixels. To obtain n-squared intensity levels, we set up an n by n dither matrix Dn, whose elements are distinct positive integers in the range 0 to n squared minus 1. For example, we can generate 4 intensity levels with this equation, and we can generate 9 intensity levels with the following matrix. The matrix elements for D2 and D3 are in the same order as the pixel mask for setting up 2 by 2 and 3 by 3 pixel grids, respectively. For a bi-level system, we then determine display intensity values by comparing input intensities to the matrix elements. Each input intensity is first scaled to the range 0 is less than or equal to I is less than or equal to n squared. If the intensity I is to be applied to screen position x, y, we can calculate row and column numbers for the dither matrix as I equals x mod n plus 1, j equals y mod n plus 1. If I is greater than dn I, j, we turn on the pixel at position x, y. Otherwise, the pixel is not turned on. Elements of the dither matrix are assigned to in accordance with the guidelines discussed for pixel grids. That is, we want to minimize added visual effect in a displayed scene. Ordered dither produces constant intensity areas identical to those generated with pixel grid patterns when the values of the matrix elements correspond to the grid mask. Variations from the pixel grid display occur at boundaries of the intensity levels. Typically, the number of intensity levels is taken to be a multiple of 2. Higher order dither matrices are then obtained from lower order matrices with a recurrence relation. Assuming n to be greater or equal to 4. Parameter un by 2 is a unity matrix. All elements are 1. As an example, if D2 is specified, then recurrence relation yields. Another method for mapping a picture with m by n points to a display area with m by n pixels is error diffusion. Here the error between an input intensity value and the displayed pixel intensity level at a given position is dispersed or diffused to pixel positions to the right and below the current pixel position. Starting with the matrix M of intensity values obtained by scanning a photograph, we want to construct an array I of pixel intensity values for an area of the screen. We do this by first scanning across the rows of M from left to right, top to bottom, and determining the nearest available pixel intensity level for each element of M. Then the error between the values stored in matrix M and the displayed intensity level at each pixel position is distributed to neighboring elements in M using the following simplified algorithm. Once the elements of matrix I have been assigned intensity level values, we then map the matrix to some area of a display device, such as a printer or video monitor. Of course, we cannot disperse the error past the last matrix column, j equals n, or below the last matrix row, I equals m. For a bi-level system, the available intensity levels are 0 and 1. Parameters for distributing the error can be chosen to satisfy the following relationship. Alpha plus beta plus gamma plus delta is equal or less than 1. One choice for the error diffusion parameters that produces fairly good results is alpha, beta, gamma, delta equaling 7 by 16, 3 by 16, 5 by 16 and 1 by 16. This figure illustrates the error distribution using these parameter values. Error diffusion sometimes produces ghosts in a picture by repeating or echoing certain parts of the picture, particularly with facial features such as hairlines and nose outlines. Ghosting can be reduced by choosing values for the error diffusion parameters that sum to a value less than 1 and by rescaling the matrix values after the dispersion of errors. One way to rescale is to multiply all elements of M by 0.8 and then add 0.1. Another method for improving picture quality is to alternate the scanning of matrix rows from right to left and left to right. A variation on the error diffusion method is dot diffusion. In this method, the M by N array of intensity values is divided into 64 classes numbered from 0 to 63 as shown in this figure. The error between a matrix value and the displayed intensity is then distributed only to those neighboring matrix elements that have a larger class number. Distribution of the 64 class numbers is based on minimizing the number of elements that are completely surrounded by elements with a lower class number, since this would tend to direct all errors of the surrounding elements to that one position. Intensity attenuation. As radiant energy from a point light source travels through space, its amplitude is attenuated by the factor 1 by d squared, where d is the distance that the light has traveled. This means that the surface close to the light source, small d, receives a higher incident intensity from the source than a distant surface, large D. Therefore, to produce realistic lighting effects, our illumination model should take this intensity attenuation into account. Otherwise, we are illuminating all surfaces with the same intensity, no matter how far they might be from the light source. If two parallel surfaces with the same optical parameters overlap, they would be indistinguishable from each other. The two surfaces would be displayed as one surface. Our simple point source illumination model, however, does not always produce realistic pictures if we use the factor 1 by d squared to attenuate intensities. The factor 1 by d squared produces too much intensity variations when d is small, and it produces very little variation when d is large. This is because real scenes are usually not illuminated with point light sources, and our illumination model is too simple to accurately describe real lighting effects. Graphics packages have compensated for these problems by using inverse linear or quadratic functions of d to attenuate intensities. For example, a general inverse quadratic attenuation function can be set up as f of d equals 1 over a naught plus a1d plus a2d squared. A user can then fiddle with the coefficients a0, a1 and a2 to obtain a variety of lighting effects for a scene. The value of the constant term a0 can be adjusted to prevent function d from becoming too large when d is very small. Also, the values for the coefficients in the attenuation function and the optical surface parameters for a scene can be adjusted to prevent calculations of reflected intensities from exceeding the maximum allowable value. This is an effective method for limiting intensity values when a single light source is used to illuminate a scene. For multiple light source illumination, the methods described in the preceding section are more effective for limiting the intensity range. With a given set of attenuation coefficients, we can limit the magnitude of the attenuation function to 1 with the calculation f of d equals min of 1 and 1 over a0 plus a1d plus a2d squared. Using this function, we can then write our basic illumination models as shown on the screen, where di is the distance light has traveled from light source I. Polygon rendering methods, Gouraud and Phong shading. Each polygon can be rendered with a single intensity, or the intensity can be obtained at each point of the surface using an interpolation scheme. Gouraud shading. This intensity interpolation scheme, developed by Gouraud and generally referred to as Gouraud shading, renders a polygon surface by linearly interpolating intensity values across the surface. Intensity values for each polygon are matched with the values of adjacent polygons along the common edges, thus eliminating the intensity discontinuities that can occur in flat shading. Each polygon surface is rendered with Gouraud shading by performing the following calculations. Determine the average unit normal vector at each polygon vertex. Apply an illumination model to each vertex to calculate the vertex intensity. Linearly interpolate the vertex intensities over the surface of the polygon. At each polygon vertex, we obtain a normal vector by averaging the surface normals of all polygons sharing that vertex, as illustrated in this figure. Thus, for any vertex position V, we obtain the unit vertex normal with the calculation as shown. Once we have the vertex normals, we can determine the intensity at the vertices from a lighting model. This figure demonstrates the next step, interpolating intensities along the polygon edges. For each scan line, the intensity at the intersection of the scan line with the polygon edges linearly interpolated from the intensities at the edge endpoints. For example, in this figure, the polygon edge with endpoint vertices at positions 1 and 2 is intersected by the scan line at point 4. A fast method for obtaining the intensity at point 4 is to interpolate between intensities I1 and I2 using only the vertical displacement of the scan line. Similarly, intensity at the right intersection of this scan line, point 5, is interpolated from intensity values at vertices 2 and 3. Once these bounding intensities are established for a scan line, an interior point is interpolated from the bounding intensities at points 4 and 5 as incremental calculations are used to obtain successive edge intensity values between scan lines and to obtain successive intensities along a scan line. As shown in this figure, if the intensity at edge position x, y is interpolated as I equals y minus y2 over y1 minus y2 into I1 plus y1 minus y over y1 minus y2 into I2, then we can obtain the intensity along this edge for the next scan line, y minus 1, as I dash equals I plus I2 minus I1 over y1 minus y2. Similar calculations are used to obtain intensities at successive horizontal pixel positions along each scan line. When surfaces are to be rendered in color, the intensity of each color component is calculated at the vertices. Gouraud shading can be combined with the hidden surface algorithm to fill in the visible polygons along each scan line. An example of an object shaded with Gouraud method appears in this figure. Gouraud shading removes the intensity discontinuities associated with the constant shading model. Deficiencies of Gouraud shading. Highlights on the surface are sometimes displayed with anomalous shapes, and the linear intensity interpolation can cause bright or dark intensity streaks called Mach bands to appear on the surface. These effects can be reduced by dividing the surface into a greater number of polygon faces or by using other methods such as Phong shading that require more calculations. Phong shading. A more accurate method for rendering a polygon surface is to interpolate normal vectors and then apply the illumination model to each surface point. This method, developed by Phong Bui Truong, is called Phong shading or normal vector interpolation shading. It displays more realistic highlights on a surface and greatly reduces the Mach band effect. A polygon surface is rendered using Phong shading by carrying out the following steps. Determine the average unit normal vector at each polygon vertex. Linearly interpolate the vertex normals over the surface of the polygon. Apply an illumination model along each scan line to calculate projected pixel intensities for the surface points. Interpolation of surface normals along a polygon edge between two vertices is illustrated in this figure. The normal vector n for the scan line intersection point along the edge between vertices 1 and 2 can be obtained by vertically interpolating between edge endpoint normals. N equals y minus y2 over y1 minus y2 into n1 plus y1 minus y over y1 minus y2 into n2. Incremental methods are used to evaluate normals between scan lines and along each individual scan line. At each pixel position along a scan line, the illumination model is applied to determine the surface intensity at that point. Intensity calculations using an approximate normal vector at each point along the scan line produce more accurate results than the direct interpolation of intensities, as in Gauss shading. The trade-off is that Phong shading requires considerably more calculations. Fast Phong shading. Surface rendering with Phong shading can be speeded up by using approximations in the illumination model calculations of normal vectors. Fast Phong shading approximates the intensity calculations using a Taylor series expansion and triangular surface patches. Since Phong shading interpolates normal vectors from vertex normals, we can express the surface normal n at any point x, y over a triangle as n equals ax plus by plus c, where vectors a, b, and c are determined from the three vertex equations nk equals axk plus byk plus c, k equals to 1, 2, and 3, with the xk, yk denoting a vertex position. Omitting the reflectivity and attenuation parameters, we can write the calculation for light source diffuse reflection from a surface point x, y as shown on screen. We can rewrite this expression in the form I diff x, y equals ax plus by plus c over dx squared plus exy plus fy squared plus gx plus hy plus I raised to the power of 1 by 2, where parameters such as a, b, c, and d are used to represent the various dot products. For example, a equals L and a over mod L. Finally, we can express the denominator as a Taylor series expansion and return terms up to second degree in x and y. This yields I diff x, y equals t5x squared plus t4xy plus t3y squared plus t2x plus t1y plus t0, where each tk is a function of parameters a, b, and c, and so forth. Using forward differences, we can evaluate this equation with only two additions for each pixel position x, y once the initial forward difference parameters have been evaluated. Although fast Phong shading reduces the Phong shading calculations, it still takes approximately twice as long to render a surface with fast Phong shading as it does with Gauss shading. Normal Phong shading using forward differences takes about 6 to 7 times longer than Gauss shading. Fast Phong shading for diffuse reflection can be extended to include specular reflections. Calculations similar to those for diffuse reflections are used to evaluate specular terms such as n and h raised to the power n in the basic illumination model. In addition, we can generalize the algorithm to include polygons other than triangles and finite viewing positions. Problems with interpolated shading. There are many problems common to all these interpolated shading models, several of which we list here. Polygonal silhouette. No matter how good an approximation an interpolated shading model offers to the actual shading of a curved surface, the silhouette edge of the mesh is still clearly polygonal. We can improve the situation by breaking the surface into a greater number of smaller polygons, but at a corresponding increase in expense. Perspective distortion. Anomalies are introduced because interpolation is performed after perspective transformation in the 3D screen coordinate system. For example, linear interpolation causes the shading information in this figure to be incremented by a constant amount from one scan line to another along each edge. Consider what happens when vertex 1 is more distant than vertex 2. Perspective foreshortening means that the difference from one scan line to another in the untransformed z value along an edge increases in the direction of the farther coordinate. Thus, if ys equals y1 plus y2 over 2, then is equals I1 plus I2 over 2, but zs will not equal z1 plus z2 over 2. This problem can also be reduced by using a larger number of smaller polygons. Decreasing the size of the polygons increases the number of points at which the information to be interpolated is sampled, and therefore increases the accuracy of the shading. Orientation dependence. The results of interpolated shading models are not independent of the projected polygon's orientation. Since values are interpolated between vertices and across horizontal scan lines, the results may differ when the polygon is rotated. See this figure. This effect is particularly obvious when the orientation changes slowly between successive frames of an animation. A similar problem can also occur in visible surface determination when the Z value at each point is interpolated from the Z values assigned to each vertex. Both problems can be solved by decomposing polygons into triangles. Alternatively, Duff suggests rotation-independent but expensive interpolation methods that solve this problem without the need for decomposition. Problems at shared vertices. Shading discontinuities can occur when two adjacent polygons fail to share a vertex that lies along their common edge. Consider the three polygons of this figure, in which vertex C is shared by the two polygons on the right, but not by the large polygon on the left. The shading information determined directly at C for the polygons at the right will typically not be the same as the information interpolated at that point from the values at A and B for the polygon at the left. As a result, there will be discontinuity in the shading. The discontinuity can be eliminated by inserting in the polygon on the left an extra vertex that shares C's shading information. We can pre-process a static polygonal database in order to eliminate this problem. Alternatively, if polygons will be split on the fly, that is, using the BSP tree visible surface algorithm, then extra bookkeeping can be done to introduce a new vertex in an edge that shares an edge that is split. Unrepresentative vertex normals. Computed vertex normals may not adequately represent the surface's geometry. For example, if we compute the vertex normals by averaging the normals of the surfaces sharing a vertex, all of the vertex normals of this figure will be parallel to one another, resulting in little or no variation in shade if the light source is distant. Subdividing the polygons further before the vertex normal computation will solve this problem. Although these problems have prompted much work on rendering algorithms that handle curved surfaces directly, polygons are sufficiently faster and easier to process that they still form the core of most rendering systems. Ray tracing methods. Ray casting, where a ray is sent out from each pixel position to locate surface intersections for object modeling using constructive solid geometry methods. The use of ray casting is a method for determining visible surfaces in a scene. Ray tracing is an extension of this basic idea. Instead of merely looking for the visible surface for each pixel, we continue to bounce a ray around the scene, as illustrated in this figure, collecting intensity contributions. This provides a simple and powerful rendering technique for obtaining global reflection and transmission effects. The basic ray tracing algorithm also provides for visible surface detection, shadow effects, transparency, and multiple light source illumination. Many extensions to the basic algorithm have been developed to produce photorealistic displays. Ray traced displays can be highly realistic, particularly for shiny objects, but they require considerable computation time to generate. An example of the global reflection and transmission effects possible with ray tracing is shown in this figure. Basic ray tracing algorithm. We first set up a coordinate system with the pixel positions designated in the XY plane. The scene description is given in this reference frame. Refer figure. From the center of projection, we then determine a ray path that passes through the center of each screen pixel position. Illumination effects accumulated along this ray path are then assigned to the pixel. This rendering approach is based on the principles of geometric optics. Light rays from the surfaces in a scene emanate in all directions, and some will pass through the pixel positions in the projection plane. Since there are an infinite number of ray paths, we determine the contributions to a particular pixel by tracing a light path backward from the pixel to the scene. We first consider the basic ray tracing algorithm with one ray per pixel, which is equivalent to viewing the scene through a pinhole camera. For each pixel ray, we test each surface in the scene to determine if it is intersected by the ray. If a surface is intersected, we calculate the distance from the pixel to the surface intersection point. The smallest calculated intersection distance identifies the visible surface for that pixel. We then reflect the ray off the visible surface along a specular path. Angle of reflection equals angle of incidence. If the surface is transparent, we also send a ray through the surface in the refraction direction. Reflection and refraction rays are referred to as secondary rays. This procedure is repeated for each secondary ray. Objects are tested for intersection, and the nearest surface along a secondary ray path is used to recursively produce the next generation of reflection and refraction paths. As the rays from a pixel ricochet through the scene, each successively intersected surface is added to a binary ray tracing tree as shown in this figure. Left branches in the tree to represent reflection paths. Right branches represent transmission paths. Maximum depth of the ray tracing trees can be set as a user option, or it can be determined by the amount of storage available. A path in the tree is then terminated if it reaches the preset maximum or if the ray strikes a light source. The intensity assigned to a pixel is then determined by accumulating the intensity contributions starting at the bottom terminal nodes of its ray tracing tree. Surface intensity from each node in the tree is attenuated by the distance from the parent surface, next node up the tree, and added to the intensity of the parent surface. Pixel intensity is then the sum of the attenuated intensities at the root node of the ray tree. If no surfaces are intersected by a pixel ray, the ray tracing tree is empty and the pixel is assigned the intensity value of the background. If a pixel ray intersects a non-reflecting light source, the pixel can be assigned the intensity of the source, although light sources are usually placed beyond the path of the initial rays. This figure shows a surface intersected by a ray and the unit vectors needed for the reflected light intensity calculations. Unit vector u is in the direction of the ray path. N is the unit surface normal. R is the unit reflection vector. L is the unit vector pointing to the light source. And H is the unit vector halfway between V, opposite to U, and L. The path along the L is referred to as the shadow ray. If any object intersects the shadow ray between the surface and the point light source, the surface is in shadow with respect to that source. Ambient light at the surface is calculated as Ka into Ia. Diffuse reflection due to the source is proportional to Kd of N and L, and the specular reflection component is proportional to Ks into H and N raised to the power Ns. The specular reflection direction for the secondary ray path R depends on the surface normal and the incoming ray direction. R equals U minus 2U and N into N. For a transparent surface, we also need to obtain intensity contributions from light transmitted through the material. We can locate the source of this contribution by tracing a secondary ray along the transmission direction T as shown in the figure. The unit transmission vector can be obtained from vectors U and N as T equals eta I over eta R into U minus cos theta R minus eta I over eta R into cos theta I into N. Parameters eta I and eta R are the indices of refraction in the incident material and the refracting material, respectively. Angle of refraction theta R can be calculated from Snell's law as cos theta R equals to square root of 1 minus eta I over eta R whole squared into 1 minus cos squared theta I. Ray surface intersection calculations. A ray can be described with an initial position P0 and the unit direction vector U as illustrated in this figure. The coordinates of any point P along the ray at a distance s from P0 is computed from the ray equation P equals P0 plus SU. Initially, P0 can be set to the position of the pixel on the projection plane, or it could be chosen to be the projection reference point. Unit vector U is initially obtained from the position of the pixel through which the ray passes and the projection reference point. U equals P pix minus P PRP over mod of P pix minus P PRP. At each intersected surface, vectors P0 and U are updated for the secondary rays at the ray surface intersection point. For the secondary rays, reflection direction for U is R and the transmission direction is T. To locate surface intersections, we simultaneously solve the ray equation and the surface equation for the individual objects in the scene. The simplest objects to ray trace are spheres. If we have a sphere of radius r and center position PC, refer this figure, then any point P on the surface must satisfy the sphere equation. Mod of P minus PC whole squared minus r squared equals 0. Substituting the ray equation, then we have mod of P0 plus SU minus PC whole squared minus r squared equals 0. If we let delta P equals PC minus P0 and expand the dot product, we obtain the quadratic equation. S squared minus 2U and delta P into S plus mod of delta P squared minus R squared equals 0, whose solution is S equals U into delta P plus or minus square root of U and delta P squared minus mod delta P squared plus R squared. If the discriminant is negative, the ray does not intersect the sphere. For small spheres that are far from the initial ray position, this is susceptible to round-off errors. That is, if R squared is much less than mod of delta P squared, we could lose the R squared term in the precision error of mod of delta P squared. We can avoid this for most cases by rearranging the calculation for distance S as S equals U and delta P plus or minus square root of R squared minus mod of delta P minus U and delta P into U whole squared. This figure shows a snowflake pattern of shiny spheres rendered with ray tracing to display global surface reflections. Polyhedra require more processing than spheres to locate surface intersections. For that reason, it is often better to do an initial intersection test on a bounding volume. For example, this figure shows a polyhedron bounded by a sphere. If a ray does not intersect the sphere, we do not need to do any further testing on the polyhedron. But if the ray does intersect the sphere, we first locate the front faces with the test U and n is less than 0, where n is a surface normal. For each face of the polyhedron that satisfies this inequality, we solve the plane equation n and p equals minus d. For surface position P, that also satisfies the ray equation. Here n equals a, b, c, and d is the fourth plane parameter. Position P is both on the plane and on the ray path if n and P0 plus SU equal to minus d, and the distance from the initial ray position to the plane is S equals minus d plus n and P0 over n and u. This gives us the position on the infinite plane that contains the polygon face, but this position may not be inside the polygon boundaries. Refer this figure. So we need to perform an inside-outside test to determine whether the ray intersected this face of the polyhedron. We perform this test for each face satisfying inequality. The smallest distance S to an inside point identifies the intersected face of the polyhedron. If no intersection positions are inside points, the ray does not intersect the object. Similar procedures are used to calculate ray surface intersection positions for other objects, such as quadric or spline surfaces. We combine the ray equation with the surface definition and solve for parameter S. In many cases, numerical root finding methods and incremental calculations are used to locate intersection points over a surface. This figure shows a ray trace scene containing multiple objects and the texture patterns. Reducing object intersection calculations. Ray surface intersection calculations can account for as much as 95% of the processing time in a ray tracer. For a scene with many objects, most of the processing time for each ray is spent in checking objects that are not visible along the ray path. Therefore, several methods have been developed for reducing the processing time spent on these intersection calculations. One method for reducing the intersection calculations is to enclose groups of adjacent objects within a bounding volume, such as a sphere or a box. See this figure. We can then test for ray intersections with the bounding volume. If the ray does not intersect the bounding object, we can eliminate the intersection tests with the enclosed surfaces. This approach can be extended to include a hierarchy of bounding volumes. That is, we enclose several bounding volumes within a larger volume and carry out the intersection tests hierarchically. First, we test the outer bounding volume, then if necessary, we test the smaller inner bounding volumes, and so on. Space subdivision methods. Another way to reduce intersection calculations is to use space subdivision methods. We can enclose a scene within a cube, then we successively subdivide the cube until each subregion or cell contains no more than a preset maximum number of surfaces. For example, we could require that each cell contain no more than one surface. If parallel and vector processing capabilities are available, the maximum number of surfaces per cell can be determined by the size of the vector registers and the number of processors. Space subdivision of the cube can be stored in an octree or in a binary partition tree. In addition, we can perform a uniform subdivision by dividing the cube into 8 equal size octants at each step, or we can perform an adaptive subdivision and subdivide only those regions of the cube containing objects. We then trace rays through the individual cells of the cube, performing intersection tests only within those cells containing the surfaces. The first object surface intersected by a ray is a visible surface for that ray. There is a trade-off between the cell size and the number of surfaces per cell. If we set the maximum number of surfaces per cell too low, cell size can become so small that much of the savings in reduced intersection tests goes into cell traversal processing. This figure illustrates the intersection of a pixel ray with the front face of the cube enclosing a scene. Once we calculate the intersection point on the front face of the cube, we determine the initial cell intersection by checking the intersection coordinates against the cell boundary positions. We then need to process the ray through the cells by determining the entry and exit points, refer the following figure, for each cell traversed by the ray until we intersect an object surface or exit the cube enclosing the scene. Given a ray direction U and a ray entry position P in for a cell, the potential exit faces are those for which U and Nk is greater than 0. If the normal vectors for the cell faces are aligned with the coordinate axis, then we have, and we only need to check the sign of each component of U to determine the 3 candidate exit planes. The exit position on each candidate plane is obtained from the ray equation. P out, k is equal to P in plus Sk into U, where Sk is the distance along the ray from P in to P out, k. Substituting the ray equation into the plane equation for each cell face, Nk and P out, k equals minus dk. We can solve for the ray distance to each candidate exit face as Sk equals minus d minus Nk and P in over Nk and U, and then select smallest Sk. This calculation can be simplified if the normal vectors Nk are aligned with the coordinate axes. For example, if a candidate normal vector is 1, 0, 0, then for that plane we have Sk equals Xk minus X0 over Ux, where U equals Ux, Uy, Uz, and Xk is the value for the right boundary phase for the cell. Various modifications can be made to the cell traversal procedures to speed up the processing. One possibility is to take a trial exit plane K as the one perpendicular to the direction of the largest component of U. The sector on the trial plane, refer this figure, containing P out, K, determines the true exit plane. If the intersection point is in sector 0, the trial plane is the true exit plane and we are done. If the intersection point is sector 1, the true exit plane is the top plane and we simply need to calculate the exit point on the top boundary of the cell. Similarly, sector 3 identifies the bottom plane as the true exit plane, and sectors 4 and 2 identify the true exit plane as the left and right cell planes, respectively. When the trial exit point falls in sector 5, 6, 7 or 8, we need to carry out 2 additional intersection calculations to identify the true exit plane. Implementation of these methods on parallel vector machines provides further improvements in performance. The scene in this figure was ray traced using space subdivision methods. Without space subdivision, the ray tracing calculations took 10 times longer. Eliminating the polygons also speeded up the processing. For a scene containing 2048 spheres and no polygons, the same algorithm executed 46 times faster than the basic ray tracer. This figure illustrates another ray traced scene using spatial subdivision and parallel processing methods. This image of Rodin's thinker was ray traced with over 1.5 million rays in 24 seconds. The scene shown in next figure was rendered with the light buffer technique, a form of spatial partitioning. Here a cube is centered on each point light source, and each side of the cube is partitioned with a grid of squares. A sorted list of objects that are visible to the light through each square is then maintained by the ray tracer to speed up processing of shadow rays. To determine surface illumination effects, the square for each shadow ray is computed and the shadow ray is then processed against the list of objects for that square. Intersection tests in ray tracing programs can also be reduced with directional subdivision procedures by considering sectors that contain a bundle of rays. Within each sector, we can sort surfaces in depth order, as in this figure. Each ray then only needs to test objects within the sector that contains that ray. Anti-aliased ray tracing. 2 basic techniques for anti-aliasing in ray tracing algorithms are supersampling and adaptive sampling. In supersampling and adaptive sampling, the pixel is treated as a finite square area instead of a single point. Supersampling uses multiple evenly spaced rays samples over each pixel area. Adaptive sampling uses unevenly spaced rays in some regions of the pixel area. For example, more rays can be used near object edges to obtain a better estimate of the pixel intensities. Another method for sampling is to randomly distribute the rays over the pixel area. When multiple rays per pixel are used, the intensities of the pixel rays are averaged to produce the overall pixel intensity. This figure illustrates a simple supersampling procedure. Here, one ray is generated through each corner of the pixel. If the intensities for the 4 rays are not approximately equal, or if some small object lies between the 4 rays, we divide the pixel area into subpixels and repeat the process. As an example, the pixel in this figure is divided into 9 subpixels using 16 rays, one at each subpixel corner. Adaptive sampling is then used to further subdivide those subpixels that do not have nearly equal intensity rays or that subtend some small object. This subdivision process can be continued until each subpixel has approximately equal intensity rays or an upper bound, say 256, has been reached for the number of rays per pixel. An extended light source was used to provide realistic soft shadows. Nearly 26 million primary rays were generated, with 33.5 million shadow rays and 67.3 million reflection rays. Wood grain and marble surface patterns were generated using solid texturing methods with a noise function. Total rendering time with the extended light source was 213 hours. Instead of passing rays through pixel corners, we can generate rays through subpixel centers, as in this figure. Another method for anti-aliasing displayed scenes is to treat a pixel ray as a cone, as shown in this figure. Only one ray is generated per pixel, but the ray now has a finite cross-section. To determine the percent of pixel area coverage with objects, we calculate the intersection of the pixel cone with the object surface. For a sphere, this requires finding the intersection of two circles. For a polyhedron, we must find the intersection of a circle with a polygon. Distributed ray tracing. This is a stochastic sampling method that randomly distributes rays according to the various parameters in an illumination model. Illumination parameters include pixel area, reflection and refraction directions, camera lens area, and time. Aliasing effects are thus replaced with low-level noise, which improves picture quality and allows more accurate modeling of surface gloss and translucency, finite camera apertures, finite light sources, and motion blur displays of moving objects. Distributed ray tracing, also referred to as distribution ray tracing, essentially provides a Monte Carlo evaluation of the multiple integrals that occur in an accurate description of a surface lighting. Pixel sampling is accomplished by randomly distributing a number of rays over the pixel surface. Choosing ray positions completely at random can result in the rays clustering together in a small region of the pixel area and leaving other parts of the pixel unsampled. A better approximation of the light distribution over a pixel area is obtained by using a technique called jittering on a regular subpixel grid. This is usually done by initially dividing the pixel area, a unit square, into the 16 sub-areas shown in this figure and generating a random jitter position in each sub-area. The random ray positions are obtained by jittering the center coordinates of each sub-area by small amounts delta x and delta y, where both delta x and delta y are assigned values in the interval minus 0.5, 0.5. We then choose the ray position in a cell with center coordinates x, y as a jitter position x plus delta x, y plus delta y. Integer codes 1 through 16 are randomly assigned to each of the 16 rays, and a table lookup is used to obtain values for the other parameters, reflection angle, time, etc. Each subpixel ray is then processed through the scene to determine the intensity contribution for that ray. The 16 ray intensities are then averaged to produce the overall pixel intensity. If the subpixel intensities vary too much, the pixel is further subdivided. To model camera lens effects, we set a lens of assigned focal length f in front of the projection plane and distribute the subpixel rays over the lens area. Assuming we have 16 rays per pixel, we can subdivide the lens area into 16 zones. Each ray is then sent to the zone corresponding to its assigned code. The ray position within the zone is set to a jittered position from the zone center. Then the ray is projected into the scene from the jittered zone position through the focal point of the lens. We locate the focal point for a ray at a distance f from the lens along the line from the center of the subpixel through the lens center, as shown in this figure. Objects near the focal plane are projected as sharp images. Objects in front or in back of the focal plane are blurred. To obtain better displays of out-of-focus objects, we increase the number of subpixel rays. Ray reflections at surface intersection points are distributed about the specular reflection direction r according to the assigned ray codes. Refer this figure. The maximum spread about r is divided into 16 angular zones, and each ray is reflected in a jittered position from the zone center corresponding to its integer code. We can use a Phong model cos raised to the power ns phi to determine the maximum reflection spread. If the material is transparent, refracted rays are distributed about the transmission direction T in a similar manner. Extended light sources are handled by distributing a number of shadow rays over the area of the light source as demonstrated in this figure. The light source is divided into zones and shadow rays are assigned jitter directions to the various zones. Additionally, zones can be weighted according to the intensity of the light source within that zone and the size of the projected zone area onto the object surface. More shadow rays are then sent to zones with higher weights. If some shadow rays are blocked by opaque objects between the surface and the light source, a penumbra is generated at that surface point. This figure illustrates the regions for the umbra and penumbra on a surface partially shielded from a light source. We create motion blur by distributing rays over time. A total frame time and the frame time subdivisions are determined according to the motion dynamics required for the scene. Time intervals are labeled with integer codes, and each ray is assigned to a jittered time within the interval corresponding to the ray code. Objects are then moved to their positions at that time, and the ray is traced through the scene. Additional rays are used for highly blurred objects. To reduce calculations, we can use bounding boxes or spheres for initial ray intersection tests. That is, we move the bounding object according to the motion requirements and test for intersection. If the ray does not intersect the bounding object, we do not need to process the individual surfaces within the bounding volume. This figure shows a scene displayed with motion blur. This image was rendered using distributed ray tracing with 40% by 3550 pixels and 16 rays per pixel. In addition to the motion blurred reflections, the shadows are displayed with penumbra areas resulting from the extended light sources around the room that are illuminating the pool table. Additional examples of objects rendered with distributed ray tracing methods are given in these figures. This figure illustrates focusing, refraction, and anti-aliasing, effects with distributed ray tracing. Solved problems. Describe how hidden surface removal and projection are integrated into the ray tracing process. Each primary ray plays the role of a projector that maps a surface point P to its image P' in the view plane. If all primary rays emanate from a viewpoint C, we have the effect of perspective projection. If all primary rays are parallel to each other, we have the effect of parallel projection. Furthermore, if a primary ray intersects several object surfaces, only the surface that is the closest to the view plane is chosen to determine the color of the corresponding pixel. All others are effectively treated as hidden surfaces and removed, not displayed. What is the difference between a vector and a ray? A vector is defined by its direction and magnitude, whereas a ray is determined by its direction and starting point. Let the viewpoint be at A, B, C, and the center of a pixel at X, Y, Z. Find vectors S and D to represent the corresponding primary ray. S equals AI plus BJ plus CK. D equals X minus A into I plus Y minus B into J plus Z minus C into K. Shadows. Hidden surface methods can be used to locate areas where light sources produce shadows. By applying a hidden surface method with the light source at the view position, we can determine which surface sections cannot be seen from the light source. These are the shadow areas. Once we have determined the shadow areas for all light sources, the shadows could be treated as surface patterns and stored in pattern arrays. This figure illustrates a generation of shading patterns for two objects on a table and a distant light source. All shadow areas in this figure are surfaces that are not visible from the position of the light source. Shadow patterns generated by a hidden surface method are valid for any selected viewing position as long as the light source positions are not changed. Surfaces that are visible from the view position are shaded according to the lighting model which can be combined with texture patterns. We can display shadow areas with ambient light intensity only, or we can combine the ambient light with specified surface textures. Specular reflection and Phong model. When we look at an illuminated shiny surface, such as polished metal, an apple, or a person's forehead, we see a highlight or bright spot at certain viewing directions. This phenomenon, called specular reflection, is the result of total or near total reflection of the incident light in a concentrated region around the specular reflection angle. This figure shows the specular reflection direction at a point on the illuminated surface. The specular reflection angle equals the angle of the incident light with the two angles measured on opposite sides of the unit normal surface vector n. In this figure, we use r to represent the unit vector in the direction of ideal specular reflection, L to represent the unit vector directed toward the point light source, and V as a unit vector pointing to the viewer from the surface position. Angle phi is the viewing angle relative to the specular reflection direction r. For an ideal reflector, perfect mirror, incident light is reflected only in the specular reflection direction. In this case, we would only see reflected light when vectors v and r coincide. Phi equals 0. Objects other than ideal reflectors exhibit specular reflections over a finite range of viewing positions around vector r. Shiny surfaces have narrow specular reflection range and dull surfaces have wider reflection range. An empirical model for calculating the specular reflection range developed by Phong Chuang and called the Phong specular reflection model, or simply the Phong model, sets the intensity of specular reflection proportional to cos ns phi. Angle phi can be assigned values in the range 0 to 90 degrees so that cos phi varies from 0 to 1. The value assigned to specular reflection parameter ns is determined by the type of surface that we want to display. A very shiny surface is modeled with a large value for ns, say 100 or more, and smaller values down to 1 are used for duller surfaces. For a perfect reflector, ns is infinite. For a rough surface, such as chalk or cinder block, ns would be assigned a value near 1. The following two figures shows the effect of ns on the angular range for which we can expect to see specular reflections. The intensity of specular reflection depends on the material properties of the surface and the angle of incidence, as well as other factors such as the polarization and color of the incident light. We can approximately model monochromatic specular intensity variations using a specular reflection coefficient, W theta, for each surface. This figure shows the general variation of W theta over the range theta equals 0 to theta equals 90 degrees for a few materials. In general, W theta tends to increase as the angle of incident increases. At theta equals 90 degrees, W theta is equal to 1, and all of the incident light is reflected. The variation of specular intensity with angle of incidence is described by Fresnel's laws of reflection. Using the spectral reflection function W theta, we can write the Phong specular reflection model as I spec equals W theta IL cos ns phi, where IL is the intensity of the light source and phi is the viewing angle relative to the specular reflection direction r. Transparent materials such as glass only exhibit appreciable specular reflections as theta approaches 90 degrees. At theta equals 0, about 4% of the incident light on a glass surface is reflected, and for most of the range of theta, the reflected intensity is less than 10% of the incident intensity. But for many opaque materials, specular reflection is nearly constant for all incidence angles. In this case, we can reasonably model the reflected light effects by replacing W theta with a constant specular reflection coefficient Ks. We then simply set Ks equal to some value in the range 0 to 1 for each surface. Since V and R are unit vectors in the viewing and specular reflection directions, we can calculate the value of cos phi with the dot product V into R. Assuming the specular reflection coefficient is a constant, we can determine the intensity of the specular reflection at a surface point with the calculation I spec equals Ks into IL into V and R raised to the power ns. Vector R in this expression can be calculated in terms of vectors L and N. As seen in this figure, the projection of L onto the direction of the normal vector is obtained with the dot product N and L. Therefore, from the diagram we have R plus L equals 2N and L multiplied by N. And the specular reflection vector is obtained as R equals 2N and L multiplied by N minus L. This figure illustrates the specular reflections for various values of Ks and Ns on a sphere illuminated with a single point light source. A somewhat simplified Phong model is obtained by using the half-wave vector H between L and V to calculate the range of specular reflections. If we replace VR in the Phong model with the dot product NH, this simply replaces the empirical cos phi calculation with the empirical cos alpha calculation. The half-wave vector is obtained as H equals L plus V over mod of L plus V. If both the viewer and the light source are sufficiently far from the surface, both V and L are constant over the surface, and thus H is also constant for all surface points. For non-planar surfaces, NH then requires less computation than VR, since the calculation of R at each surface point involves a variable vector N. For given light source and viewer positions, vector H is the orientation direction for the surface that would produce maximum specular reflection in the viewing direction. For this reason, H is sometimes referred to as the surface orientation direction for maximum highlights. Also, if vector V is coplanar with vectors L and R and thus N, angle alpha has the value phi by 2. When V, L and N are not coplanar, alpha is greater than phi by 2 depending on the spatial relationship of the three vectors. Transparency. A transparent surface produces both reflected and transmitted light. The relative contribution of the transmitted light depends on the degree of transparency of the surface and whether any light sources or illuminated surfaces are behind the transparent surface. This figure illustrates the intensity contributions to the surface lighting for a transparent object. When a transparent surface is to be modeled, the intensity equations must be modified to include contributions from light passing through the surface. In most cases, the transmitted light is generated from reflecting objects in back of the surface, as in this figure. Reflected light from these objects passes through the transparent surface and contributes to the total surface intensity. Both diffuse and specular transmission can take place at the surfaces of a transparent object. Diffuse effects are important when a partially transparent surface, such as frosted glass, is to be modeled. Light passing through such materials is scattered so that a blurred image of background objects is obtained. Diffuse refractions can be generated by decreasing the intensity of the refracted light and spreading intensity contributions at each point on the refracting surface onto a finite area. These manipulations are time-consuming, and most lighting models employ only specular effects. Realistic transparency effects are modeled by considering light refraction. When light is incident upon a transparent surface, part of it is reflected and part is refracted. Reflection direction R and refraction direction T for a ray of light incident upon a surface with index of refraction. Because the speed of light is different in different materials, the path of the refracted light is different from that of the incident light. The direction of the refracted light, specified by the angle of refraction, is a function of the index of refraction of each material and the direction of the incident light. Index of refraction for a material is defined as the ratio of the speed of light in a vacuum to the speed of light in the material. Angle of refraction, theta r, is calculated from the angle of incidence, theta I. The index of refraction, eta I, of the incident material, usually air, and the index of refraction, eta r, of the refracting material according to Snell's law is sin theta r equals eta I over eta r sin theta I. Actually, the index of refraction of a material is a function of the wavelength of the incident light, so that the different color components of a light ray will be refracted at different angles. For most applications, we can use an average index of refraction for the different materials that are modeled in a scene. The index of refraction of air is approximately 1, and that of crown glass is about 1.5. Using these values in the above equation, with an angle of incidence of 30 degrees yields an angle of refraction of about 19 degrees. This figure illustrates the changes in the path direction for a light ray refracted through a glass object. The overall effect of the refraction is to shift the incident light to a parallel path. Since the calculations of the trigonometric functions are time-consuming, refraction effects could be modeled by simply shifting the path of the incident light a small amount. From Snell's law, we can obtain the unit transmission vector t in the refraction direction theta r as t equals eta I over eta r cos theta I minus cos theta r into n minus eta I over eta r into L, where n is the unit surface normal and L is the unit vector in the direction of the light source. Transmission vector t can be used to locate intersections of the refraction path with the objects behind the transparent surface. Including refraction effects in a scene can produce highly realistic displays, but the determination of refraction paths and object intersections requires considerable computation. Most scan-line image space methods model light transmission with approximations that reduce processing time. A simpler procedure for modeling transparent objects is to ignore the path shifts altogether. In effect, this approach assumes there is no change in the index of refraction from one material to another, so that the angle of refraction is always the same as the angle of incidence. This method speeds up the calculation of intensities and can produce reasonable transparency effects for thin polygon surfaces. We can combine the transmitted intensity I trans through a surface from a background object with the reflected intensity I reflect from the transparent surface. See figure using a transparency coefficient Kt. We assign parameter Kt a value between 0 and 1 to specify how much of the background light is to be transmitted. Total surface intensity is then calculated as I equals 1 minus Kt into I reflect plus Kt I trans. The term 1 minus Kt is the opacity factor. For highly transparent objects, we assign Kt a value near 1. Nearly opaque objects transmit very little light from background objects, and we can set Kt to a value near 0 for these materials, opacity near 1. It is also possible to allow Kt to be a function of position over the surface, so that different parts of an object can transmit more or less background intensity according to the values assigned to Kt. Transparency effects are often implemented with modified depth buffer, Z-buffer algorithms. A simple way to do this is to process opaque objects first to determine depths for the visible opaque surfaces. Then the depth positions of the transparent objects are compared to the values previously stored in the depth buffer. If any transparent surface is visible, its reflected intensity is calculated and combined with the opaque surface intensity previously stored in the frame buffer. This method can be modified to produce more accurate displays by using additional storage for the depth and other parameters of the transparent surfaces. This allows depth values for the transparent surfaces to be compared to each other as well as to the depth values of the opaque surfaces. Visible transparent surfaces are then rendered by combining their surface intensities with those of the visible and opaque surfaces behind them. Accurate displays of transparency and anti-aliasing can be obtained with the A-buffer algorithm. For each pixel position, surface patches for all overlapping surfaces are saved and sorted in depth order. Then intensities for the transparent and opaque surface patches that overlap in depth are combined in the proper visibility order to produce a final average intensity for the pixel. A depth sorting visibility algorithm can be modified to handle transparency by first sorting surfaces in depth order, then determining whether any visible surface is apparent. If you find a visible transparent surface, its reflected surface intensity is combined with the surface intensity of objects behind it to obtain the pixel intensity at each projected surface point. Solved problems. The refraction index of a medium is a ratio of the speed of light in vacuum to the speed of light in that medium. Rewrite Snell's law in terms of the speed of light in the two participating media. Let C be the speed of light in vacuum, C1 be the speed of light in the medium whose refraction index is eta 1, and C2 be the speed of light in the medium whose refraction index is eta 2. We have eta 1 equals C over C1 and eta 2 equals C over C2. Hence, Snell's law can be written as sin alpha over sin beta equals eta 2 over eta 1 equals C over C2 over C over C1 equals C1 over C2. Phong model. The Phong model provides a method for simulating studio lighting effects by controlling light intensity in different directions. Light sources are modeled as points on a reflecting surface using the Phong model for the surface points. Then the intensity in different directions is controlled by selecting values for the Phong exponent. In addition, light controls such as barn doors and spotlighting used by studio photographers can be simulated in the Phong model. Flaps are used to control the amount of light emitted by a source in various directions. Two flaps are provided for each of the X, Y, and Z directions. Spotlights are used to control the amount of light emitted within a cone, with apex at point source position. The Phong model is implemented in Figs Plus, and this figure illustrates lighting effects that can be produced with this model. Conclusion. In this chapter, we have covered the following in detail: basic illumination models, diffuse reflection, specular reflection and Phong model, Phong model, intensity attenuation, color considerations, transparency, shadows, displaying light intensities, halftone patterns and dithering techniques, polygon rendering methods, Gouraud shading, Phong shading, ray tracing methods, problems with interpolated shading, bump mapping.